Hello, this video is going to walk us through the basics of using the normal tables issued in the textbook and issued in the exam. The first thing to remember is that the normal tables show the left-hand probabilities, the probability that the variable takes a value less than or equal to the given value. Remember that this is a continuous distribution, so the probability that the variable actually equals a very precise single value is 0. So it doesn't really matter whether we're talking about less than or less than or equal to. This tail probability has a notation attached to it. So phi of minus 1.2, for instance, is the probability that the variable takes a value less than or equal to 1.2 minus 1.2. Okay, now that we know that the tables are left-hand probabilities only, let's actually look at a couple of special cases. In order to read the tables, it's very straightforward. If we want the probability that z is less than or equal to 0.67, well, that's easy. We just read across at 0.6 and read across until 0.07, and where they intersect is the actual answer, 0.7486. But what if we had 3 decimal places? What if we wanted the probability that z is less than or equal to 0.254? Well, 0.2, 0.25, so 0.25 is here, and 0.26 is here. So we have 0.5987 and 0.6026. These guys are 39 in the last 2 decimals apart, so it's about 40 apart, and we want to go to 0.254, which is 4/10 of the way through this interval. Well, 1/10 of the way through this interval is 4, so 4/10 is 16. So we want to add 16 onto this. So 16 onto that is going to be 0.6003. Linear interpolation does work. You absolutely can use it. You absolutely should use it. But as far as the AP is concerned, every question is going to be rounded to 2 decimal places, so it shouldn't be necessary unless you're using a calculator, in which case it already does the hard work for you. Okay, let's use the tables to work out example 1, find the probability that z is greater than 1.34. So whenever we're doing a normal question, you really should sketch the curve and make sure you have a clear indication of what's going on. The mean is 0, the mean is 0, and the standard deviation is 1. The standard deviation is the distance to the point of inflection, the change in curvature of the curve. So this is at 1. So 1.34 is further out. And we want the probability of it being bigger than that. So it's a right tail. The problem is that the tables only give us the left-hand probabilities. So if we can work out all this, then the answer to this is 1 minus that. So I need 1 minus what I'm going to look at in the tables, which is phi of 1.34. Well, 1.34, that should be pretty easy. 1.3, read across to the 0.04 column, and I get 0.9099. So the answer is 1 minus 0.9099, which is 0.0901. Pretty straightforward. Example 2 is a typical question where it lies between 2 well-defined values. So what I want is minus 1.8, which is way down there in the left tail, and plus 1.2, which is in the right tail but not as far out. It's a good idea to try to make these values basically correct, so we can tell straight away that this area is much bigger than this area. We of course want the area between the two. The tables can't give us the area between the two. The tables can give us the area all the way down. So if I take the area all the way down from 1.2 and subtract from it the area below minus 1.8. So what I'm going to need is the probability that minus 1.8 is less than z is less than 1.2, which is the same as the area below 1.2 minus the area below minus 1.8. So I'm looking for 1.2 and minus 1.8. Well, minus 1.8 is pretty straightforward, 0.0359, and 1.2 is also straightforward, 0.8888. So the answer is phi of 1.2, 0.8888 minus phi of minus 1.8, which was 0.0359. So the answer is 0.8529. And if we look back at the diagram, we can see 85% looks right just from the sketch. It certainly feels the right answer. So again, I stress the importance of using a sketch. This one's a little more complicated. This isn't a standard normal. This is a normal with a mean of 110 and a standard deviation of 25. So the first thing we're going to have to do is standardize and work out the z values. But before we do even that, let's have a look at what this diagram should look like. 110 is the mean, 25 is the distance to the point of inflection, so 82 is 28, so it's just below that point of inflection on the left, and 156 is 46 above, so it's way above, so it's way up here. So we want the area between the two, and as before we're going to work out the area below 146 and subtract from it the area below 82. But first we need to standardize these values. So how do we standardize it? Well, the z value is always value minus the mean over the standard deviation. How many standard deviations away from the mean the value is. For 156, it's 156 minus 110 over 25, which is 1.84, and 82 minus 110 over 25 is obviously minus 28 over 25, which is 1.12, below the mean, so it's negative. So what we're really looking for is the area below 1.84 minus the area below minus 1.12. Well, the area below minus 1.12, 1.10, 1.11, 1.12 is easy, 0.1314, and the area below 1.84, 1.801234 is 0.9671. So the answer is 0.9671 subtract 0.1314, which is 0.8357. Okay, hopefully you're getting the hang of these things now. This last question is a little more interesting. So using the same distribution as the one above, so a mean of 110 and a standard deviation of 25, I want to find a symmetric interval which captures 76% of all possible values. So 3/4, just over 3/4 of all possible values. It needs to be symmetric, so it's the same distance away. I want to find what values these need to be so that this captures the central 76%. Well, we're going to have to use the tables backwards to figure this out, but remember the probabilities in the tables are all the way down to the very bottom. So if there's 76% in the middle, then that leaves 24% unaccounted for, and if it's symmetric, that must be 12% in either tail. So if there's 12% in the top tail, the area below it must be 88%. So the Z value associated with this guy is the Z value associated with 88%. So I need to find what Z value has that property. So it's the inverse phi of 0.88. So I need to try to find 0.88 in the tables and find the Z value that generates it. So 0.88 in the tables. It's 0.8790 there and 0.8810 there. I want 0.88, which is precisely halfway between those two. So it's halfway between 1.17 and 1.18. So the answer is 1.175. So 1.175 standard deviations above the mean has 88% below it, and similarly 1.175 standard deviations below the mean has 88% above it and 12% below it. So I need to go 1.175 standard deviations either side of 110. So the values are going to be 110 plus and minus 1.175 times the standard deviation, which is 110 plus and minus 29.375. $80.625 up to 139.375, and that is the symmetric interval that we've been looking for. So hopefully that's a brief introduction to using the tables, and hopefully that all makes sense.